Hello, everyone. This is Elisa Baum, GridGain's Director of Product Marketing. We'll begin in just a moment, but first I need to conduct a little bit of housekeeping. Could you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me? And let's see here. I see hands. Great. Thank you very much. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we'll take time to answer as many questions as possible. And just for your comfort, I will make sure that everybody here gets a copy of the slides as well as a link to the recording within 48 hours after the show. I'd like to thank you for attending today's webinar, Choosing the Best in-Memory Solution for Your App. It's being presented by GridGain founder and chairman of the Apache Ignite Committee, Dmitry Sitrakian. And with that said, I'll turn the floor over to Dmitry. Go ahead, Dmitry.
All right. Thanks, Alyssa, for pronouncing my name. I know it wasn't easy. All right. Hello, everyone, and thanks for attending. A little bit about myself. I've been doing distributed computing for probably 15, maybe even longer, 15 years, maybe even longer. Started out when Globus was still around, and since then been working with various clusters and distributed transactions, distributed queries for various industries, a lot of financials, and also worked sometime at eBay, consulting on architecture, etc. So I'm one of the founders at GridGain, and I'm also a chair of Apache Ignite Project Management Committee. Okay. So what we're going to talk about today. So we're going to do a brief IMC introduction, memory computing introduction. We're going to dispel a few myths about memory computing, and then we're going to look at various products. We'll talk about various products and various types of applications that are good for memory computing. Going to look at the ecosystem, going to see where each product fits and what use cases they can solve. Look at pros and cons of those products and those solutions as well. So before we proceed, I always start off with this slide. I'm a member of Apache Ignite PMC, and I also love Apache Software Foundation. I love open source. I like contributing to open source and participating in dev lists, etc. So I want to encourage you to do the same. It's very, Apache Ignite is one of the projects that I associate with very deeply. We were the GridGain as a company was the one that donated the Apache Ignite project to Apache Software Foundation, and I was the one who wrote the first line of code in GridGain. Believe me, that line of code has been long debugged and forgotten, but I think by association, I could be considered the one who wrote the first line of Apache Ignite code. So this project is very dear to me, and I think it's one of the most interesting projects at Apache. I'm not saying the most, but it's definitely up there. Why? I mean, mainly because you get to work with interesting stuff that is on the edge of computing. You get to work with cluster computing. You get to solve problems like transactions, like distributed locking, like distributed querying, data consistency, performance, asynchronous I/O, etc., etc. Integration with other Apache software projects, or any other projects that could benefit from integration with Apache Ignite. So all those tasks are available. So whether you want to become a serious contributor or just want to get your feet wet, learn about the memory computing, learn about distributed computing, you can use Apache Ignite as your learning platform. We love contributions. We have a rigorous review process, so don't worry, you will not break anything. We have a very battle-tested, I would say, a very significant collection of tests that run in continuous integration fashion on our TeamCity servers. So before you break anything, you have to pass through a lot of checkpoints. But hopefully you will actually do provide good code and do provide well thought out architecture, and we'll follow our coding guidelines, and we'll pass through all these checks and get your code in. We love contributions, and we actually getting a lot of contributions. A lot of people are joining, so I encourage you to do the same. So before we start on defining the in-memory ecosystem, let's actually define what in-memory computing is. So in-memory computing is essentially used when you need to get high performance, when you need to get good unlimited scale. And generally, it's applied to distributed systems that need to compute and transact on data very fast. So whenever you want data consistency and whenever you want millisecond to nanosecond response times, that's when in-memory computing comes to play. So if you look a little bit at a history, and I'm not going to focus too much on this slide, just briefly. We started off in 50s with tape drives. Then 70s I would call the era of hard drives, with IBM released the first Winchester. 2000 is probably era of flash drives, when flash was introduced. And era of memory I would call 2010 and up. And the reason, what gave in-memory computing a push? If you remember, not that long ago, we didn't have 64-bit processors. We had 32-bit processors, and at that time, 32-bit processors actually had a limitation. It's not at that time. This processor do have that limitation. You can only cache 4 gigabytes. You can only address 4 gigabytes of RAM. So you can only have 4 gigabytes of addressable memory. Imagine loading a terabyte of data into a 4 gigabyte, into multiple 4 gigabyte, let's say, slots of memory or servers. You'll need a lot of servers. What if you need 2 terabytes, 10 terabytes? So it definitely didn't scale. And once the 64-bit CPUs came in, we now can address a lot more, much larger spaces. We can have terabytes, multiple terabytes in RAM. Those chips are, those memory cards are available. So essentially now we can load a lot more data in RAM, and that's what gave a push to in-memory computing. So what is memory-first architecture and what is disk-first architecture? Because we have a lot of systems that process data on disk and have a lot of systems that boast in-memory computing capabilities. How are they different? So the main difference is in the way the data is accessed, of course. If you look at disk-first architectures, which are predominantly all the databases that we know of, be that RDBMS databases or NoSQL databases, or even distributed file systems like Hadoop, HDFS. So if you look at all those systems, I mean, those are disk-first architectures. And essentially, what happens when you access data? You have an API call to get to access a byte of data, let's say. Now you have to go to operating system, go through I/O controller on operating system, and eventually touch disk and load that byte. However, we need to be mindful that disk is not a byte addressable storage. Disk is a block addressable storage. So even if you need 1 byte, you will probably load 4 kilobytes or 8 kilobytes or whatever else is the block size on your operating system is. So all of that introduces latency, and of course, that can probably be as fast as maybe hundreds of milliseconds, maybe several milliseconds to hundreds of milliseconds. We're currently actively working on adding these capabilities to in-memory storage, to in-memory platform at GridGain, and we've been doing we're almost done, and we've been doing a lot of performance testing and benchmarking. And I got to tell you, even in order to guarantee persistence to disk, you need to call fsync every now and then. And depending on how much data you need to persist to disk in a guaranteed fashion, locally on the same server, on the same operating system, fsync can take from several milliseconds to hundreds of milliseconds. So this latency varies, but it definitely is not as fast as memory. So in memory-first architecture, if we need to access a byte, all we need to do is dereference the pointer where that byte resides in memory. And that is instantaneous. We don't need to even load it. We can read it right there. Even we can even read kilobytes of data right there without loading it or processing it. We can directly access any portion of the memory. And that type of access is measured in nanoseconds. And that's why whenever you need really fast performance and whenever you need a really good scale, you generally would resort to RAM versus disk. So let's dispel a few myths about in-memory computing. So we all heard that memory is too expensive. I think probably we don't hear that as much today, but there's still a rumor. I mean, some people still believe that it's too expensive to introduce in-memory architecture into their application, into their use cases. Probably 20 years ago, I would agree with those people. I mean, probably to load a terabyte of data in memory 20 years ago would cost hundreds of thousands of dollars, if not millions. Today, we just a couple of years ago, we did a POC for a very large bank in Eastern Europe called Sberbank. It's one of our biggest customers at GridGain. And they loaded large amounts of data in memory for processing, essentially a streaming use case where you load lots of data in memory, process it, and replace it with the new data afterwards. So we were able to feed terabyte of data across 10 Dell servers. Each of them had slightly above 100 gigabyte of RAM. And all of that, including hardware, including the rack itself, which we purchased, cost us about 20K. So, and we, by the way, were able to achieve somewhere close to 1 billion of operations per second on that system. So we definitely were able to bring the performance on par with the requirements, but all of that just cost us somewhere below 20K. So memory is no longer too expensive. Memory is very affordable and is being very widely used for as a main, even in many cases as a main system of records for many use cases. So another myth, memory is not durable. Well, again, if you just take RAM, DRAM, let's say, you can claim, yes, it's not durable, it will not survive a server crash. However, nowadays, most of the systems already solve that problem. If you're using a memory computing platform, then that platform probably is already taking care of fault tolerance and scalability of your architecture. For example, Apache Ignite, a distributed in-memory data fabric, will automatically persist and load data from any type RDMS or Apache Cassandra database or any other database for that matter that you would like to integrate it with. There are also lots of new innovation coming in from flash-based memory and which now can be plugged into PCI slot and act almost like a regular DRAM. It's still going to be slower, but there's a lot of innovation and a lot of new exciting features, exciting architectures that we see coming out. I'm very excited, for example, about 3D Crosspoint from Intel, which is the first flash-based memory that is byte addressable. So we're working with Intel right now, and I'm going to be very curious to see how it performs and how it does. But those types of memory, those types of flash-based memory essentially will not be volatile. They're non-volatile and they will survive server restarts. So memory is now durable, whether at a software level or even at hardware level. Flash is fast enough. Well, I mean, that can be true for some applications and not true for others. Flash, as fast as it is, it's definitely faster than spinning hard drives, spinning disks, but it's still a block level device. So if you need to access bytes, DRAM, nothing will beat DRAM. So DRAM is still going to be about 100 times faster if not 1,000 times faster than flash-based access. However, there's also always a concept of good enough. Maybe 10 millisecond latency is good enough for your application. Then there's no need for you to get it to 1 millisecond latency or maybe half a millisecond. So you always have to weigh and compare cost to benefit here. And if you do need performance, then you should be willing to pay a little more and move your processing into DRAM. If you do not need performance, maybe flash is fast enough for you. And the last myth, memory is used only for caching. Very primitive. That's a very primitive way to look at the world. Caching is an important aspect of memory, but a lot of systems use caching just as a small feature or as a small component of their architectures. Nowadays, lots of processing happens directly in memory. We're doing machine learning in memory, we're doing streaming in memory, we're doing caching, transactions, queries in memory, etc. And that's where the products like memory data fabrics and memory data grids come in. So caching is just a very small component of in-memory architectures. Generally speaking, we see a lot more. And by the way, we'll be talking about many products within in-memory ecosystems here. So let's look at different IMC product categories. Well, what is out there? What kind of in-memory computing products can we meet? First, there are in-memory options for the database. That would be like in-memory option for Oracle database or in-memory option for Microsoft SQL Server or many other RDBMS systems. Then there are in-memory databases. Then there are in-memory data grids, in-memory data fabrics. So all these different types of products are available when you are moving into in-memory computing or choosing an in-memory computing solution. So it's important to understand what each of these categories is good for, what are pros and what are cons. So let's take a look first at in-memory options. So what are the advantages of using in-memory option for your database? Generally speaking, you're still using a database. You already wrote a lot of code for it. Your application works on it. Now you flip a switch in configuration. You added some memory. Maybe you moved it to a more powerful server with more RAM. You can allocate more memory to that server, and your queries, your database access, database performance will be better. You will not have to change any code. Your application will work out of the box if you turn on the memory option on your database. However, you're still using one server. There's no scalability here, and you're still limited to the memory that is available on one server. If you look at other memory solutions that scale out, then you can use as collectively the total memory across all the servers available in the cluster. So if you have hundreds of 10 gigabyte servers, you can cache thousands of gigabytes of RAM and memory, which is terabyte actually. So that's a memory option of for standard databases. So if you look at before we look at other available options, let's actually look at where each one of them will fall. So I specifically wanted to mention the memory option of a database before this slide because it doesn't really fit into this architectures of the future. Most projects today will start out in one way or another on a distributed scalable architecture. And standard monolithic database generally do not fit that use case, do not fit that scalability requirement. So if you look at the industry, then there is probably, I mean, in a very primitive way, we can split it in two parts: fast data and big data. So fast data is generally applies to OLTP use cases. So OLTP use cases are categorized by high throughput and low latency. So it's very important to be able to process hundreds of thousands of operations per second, and it's very important to have latencies in milliseconds if not in nanoseconds in those applications. Generally speaking, this is your operational data set. This is the data set that keeps changing as we go, as your business progresses. So you need it to be consistent, you need it to be fast, your business depends on it. So there's also big data, which type of the side of the world, which is categorized mostly by OLAP applications. So OLAP will be different from OLTP because now we do not care about high throughput anymore. OLAP is generally used for analyzing data, processing data offline in a batch-oriented fashion lots of times. And in those use cases, we still care about latency. We want it to be fast. Nobody wants their processing to be slow. But now, fast, the whole definition of fast changed, because now we want to run a query and get a result visually fast, and that probably for a human eye would be anywhere under a second. Just imagine what would happen on OLTP side of the world if every query took about half a second or a second. That would be very slow. We definitely would not be able to process hundreds of thousands of operations per second. So definitely different types of use cases, different way you interact with the system. So for OLAP, I would say that you generally should be fast enough for a human eye, and you should generally come back anywhere between in a vicinity of 1 second would be considered fast. And you're generally working with data that is offline, historical data sets. You do not care about throughput as much, but you do care about queries coming back within a second or so. So what is the ecosystem? Where do various products reside? So if you look at fast data side, you get a lot of streaming, in-memory streaming products like Apache Flink, Kafka, Apache Apex. You got in-memory data grids and fabrics like Ignite and Geode, both projects from Apache. You get in-memory database products like MemSQL and VoltDB. Those are not Apache projects. And some NoSQL like MongoDB or Apache Cassandra. On a big data side, you generally get this OLAP use case where Hadoop generally fits. So you get Apache Hadoop MapReduce, HDFS, products like SSH, and a whole slew of Apache Hadoop ecosystem projects. There are quite a few. I'm not going to mention them all here. You also have Spark. However, Spark could easily be on either side, because Spark also has streaming, which theoretically should work with your live data in memory. So Spark could we could put Spark into the streaming use case under fast data as well. But Spark also does a lot of machine learning, graph processing, a lot of scale, and the reason I actually decided to put it on a big data set because it works with mainly with offline data. Mainly, even the data is still processed in memory, you are not operating on that data in Spark. You generally will operate in some other system, which would be from a fast data side. Maybe a data grid, a data fabric, or in-memory database, or any streaming product, and then you would copy it into Spark for processing in memory. So that's why I thought that Spark should probably be on a big data side. So let's take a look at these categories. I'm going to skip through the streaming projects because they're probably a very specific use case where you just stream data and push it through a workflow. I'm mostly interested in various data access patterns for a memory project and various ways to store the data in memory. So one of the categories is in memory database. There are a couple of projects there that are well known, MemSQL and VoltDB. So why are they called in-memory database? Generally speaking, because they behave just like a database, but in memory. You do not have disk. You do not, or I mean, I should not say that. They have some persistence options, but they are memory-first architectures. And the reason they're called database is because the main way to interact with those systems is SQL. Not the main way, probably the only way to interact with those systems is SQL. So you would interact with those systems by connecting using standard database drivers, and start issuing queries or DDL, DML statements like inserts, updates, deletes, etc., creating schemas. So that's the way you interact with in-memory databases. However, by being in memory, the systems like that would probably have a very high throughput and very good scalability characteristics. However, that's on a pro side. On the con side, SQL is the only way to talk to the system, and SQL, uh, even though it's in memory, it will be faster, but SQL, you cannot always make SQL fit into all distributed use cases. Sometimes you really need to go exactly to the server where the data resides and perform some type of computation directly on the data that is residing on that server. And that's not SQL, that's plain closure execution, distributed closure execution, or maybe fork join type of computation, etc. So just providing SQL API is somewhat limiting. And another limiting factor of in-memory databases would be that essentially they become your primary system of record. You have to, if you already have a database, you have to put it aside, you have to toss it out, and put in-memory database in, the new in-memory database in. And generally speaking, that doesn't work very well with most of the companies. A lot of companies have a love and hate kind of relationship with their existing databases, but when a question comes to move to another one, it's a definite no-no. Whether we love it or hate it, there's a lot of infrastructure code around it. There's a lot of logic and processing and testing that's been put around it. So just to migrate from one database to another, it's a huge effort. And that actually makes this type of projects more feasible for new projects, for projects that are starting and just selecting a new database, and probably very poor choice for projects that have to work or accelerate existing systems based on existing databases. So sometimes a complete replacement of a database may be a good thing, sometimes a bad thing, essentially. I would say, again, if you're replacing the database, you probably something is significantly wrong in your architecture. Generally speaking, you want to accelerate your database or put some acceleration on top of it. And that's where the products like in-memory data grids or in-memory data fabric come in. By the way, I should fix this slide. Apache GeoAuth is no longer incubating. It's a top-level project. But if you look at in-memory data grids, there's always, obviously, Apache Ignite. There's Apache GeoAuth. And how are in-memory data grids are different from in-memory databases? So both, there are a lot of similarities. Let me start from the basic architecture. So both systems will distribute your data across multiple servers. However, data grids will generally provide different way to access the data. Data grids would work a lot of times with a key value API. So you can access data by key, you can store data by key. Some data grids will provide a custom query API to query the data. And given that you access data by key, data grids, a lot of data grids will always also provide a way to collocate custom computations with your data. So you can send random pieces of logic that is important to your application. Maybe you wanna go across many accounts and close the balances or perform any other type of computation. You want to do that directly on the server where data resides, and that's what data grids are very good at. They will collocate your computations with the data, and that's where very high throughput and very low latencies come in, because collocated processing is going to be always faster. Ideally, when you're working in a distributed system, the more you can collocate, the faster and more scalable your system will become. However, the disadvantage here is that unlike SQL, you do have to write code here. You do have to integrate your logic with a data grid. However, the benefit is that you get this nanosecond level or a millisecond level performance, hundreds of thousands of operations per second throughput. Lots of data grids will also support transactions, and another advantage of data grids would be that unlike in-memory databases, which essentially become your system of record, data grids will slide in on top of your database and integrate with it. So if you already have Oracle or MS SQL or maybe Cassandra database installed, a data grid would provide an API that sits between the database and your application, and will provide a lot of caching and a lot of data distribution. Here's a slide that actually kind of describes what a data grid looks like. Given that I'm mostly involved with Apache Ignite, I picked Apache Ignite architecture diagram, but it may in some way apply to other data grids as well. Many data grids, there are a couple of data grids that implement GSR 107 standard, which is a JCache standard. They're namely Apache Ignite, Oracle Coherence implements it, or Hazelcast also implements a JCache standard. But what does JCache provide? So essentially, it's a key value store. You got multiple servers. Your key set is split across those servers, and every server is responsible for storing only a portion of the keys. Collectively, across all these servers, you have your total data set. So the data can be stored in on-heap memory or off-heap memory. So obviously, when you store data in off-heap memory, your JVM does not know about it. Why do we do it? Because of garbage collection. Given that we want to cache as much data as possible, we want to be able to load hundreds of gigabytes of data in memory. However, if you try that with a regular Java app, you'll quickly notice that you will run into several minute GC pauses, garbage collection pauses. On a cluster of 5 nodes, if you load about I think 50 gigabyte of RAM on each, you can easily run into several minute GC pause. Just multiply that by 20 nodes, 30 nodes, and you'll see how much worse will your garbage collection will get. So by storing data outside of Java heap, we essentially manage that memory ourselves. But management of this memory is much easier for us than for Java, because we are operating within a certain API, like let's say it's a JCache API or HashMap API, if you will, because the API looks very close to a HashMap API. So we know when a new memory should be allocated, when you create a new entry, when you delete a new entry, when you access an entry. So all these operations are driven by an API, and therefore we can easily manage that memory by executing certain commands whenever certain API calls are executed. So it's much easier for us to manage it, and provides a huge benefit because now you don't have to worry about your garbage collection. So what does DataGrid add on top of basic JCache APIs? Mainly one of the most important features is transactions, of course. DataGrids should be fully transactional. Data should not be eventually consistent, sometimes consistent, sometimes inconsistent. Data should always be consistent. A lot of financials are using data grid applications. It's very popular in financial industry. So imagine if you had to move money from one account to another, and the data would become eventually consistent at some point. That probably would not work for most of the banking applications, and that's why data grids are very popular in financials, because of ability to process transactions in reliable fashion. Various data grids will provide different transactional semantics. Apache Ignite probably is one of the stronger data grids in this area from both performance standpoint and transactional semantic standpoint. If you know how to use Oracle transactions, then you know how to use Apache Ignite transactions. You can do optimistic, pessimistic modes. You can do read committed, repeatable read, serializable transactions. We even have a mode for deadlock-free transactions where we automatically detect deadlocks, etc. So do check it out. Very important feature. However, most of the in-memory, I should probably say that most of the in-memory databases will also support transactional. Some data grids also will provide some query API. For example, Apache Ignite is fully ANSI 99 compliant and provides and supports SQL for data access. So the question, how is it different from an in-memory database. Why, if you support SQL, you wouldn't call yourself an in-memory database? The answer here is today Apache Ignite supports everything that starts with the word select for data querying. So it's only access of the data. It's not. It's only SQL. It's not DML or DDL. So you would access data using SQL, but you still would have to store it using our streaming APIs or using our uh, key value APIs. But however, that will change going forward, and I'll talk about it a little bit. So all the indexes are stored in memory. That's very important because indexes improve performance of the queries and improve performance of the joins. If any of you have used Spark SQL before, then you probably know that Spark, for example, does not do indexes. It simply does not support indexes, and queries could take 30 minutes in Spark. I mean, I usually do a demo when I load 5 GB of data into a small Spark app I have running on my laptop, and a query on that app will, with a couple of joins in a query, will take about 30 seconds to a minute, and then I switch and run the same query on the same data set using Apache Ignite, and it returns in milliseconds. To load the data into Ignite would take longer than in Spark because we have to index it. But to query it will be a lot faster than Spark because it's already indexed. And for us, it's a hash map lookup, and for Spark, it's always full scan. That's the major performance and performance difference there. So if you actually load, if your use case would be loading data many times and querying it a few times, you'd probably use Spark in those use cases. However, if you load data rarely and you query it a lot, which is, in my experience, most of the time you would load it and then you would execute many queries on your dataset, then indexing becomes important. And we have many users who use either Ignite directly or use our integration with Apache Spark to get a performance boost for Spark applications. And as you see on this diagram, automatic RDBMS integration, or any other data storage integration for that matter. Again, the data grid will slide in between your application and your database and provide additional functionality for distributed computing and provide the scalability features and performance features to your app. Again, SQL is always important. That's why in-memory databases and in-memory data grids are all trying to support SQL as much as possible. From a data grid standpoint, I would say Ignite probably is the only data grid that supports ANSI 99 SQL. So that's where it comes close to in-memory database, but not quite because, as I mentioned, only selects are supported today. But if you're querying your data, you can connect to Ignite, for example, using JDBC or DBC drivers. The data is always consistent. The data is always fault tolerant. So even though the query is distributed, regardless of which server will crash, the result will be always consistent. And the main advantage here is that you can use distributed joins. And you can store data in multiple caches, and you can do cross-cache joins. So you can, if you define a cache as a table, essentially that would be the analogy, then you can simply select star from person and organization where person org ID equals organization ID, and then add any type of work loss and group by ident, etc. So any type of SQL would work, including all the aggregations and all the custom aggregations or group by sorting calls. All of those would work in Ignite. So from a querying standpoint, Ignite is essentially when you're trying to connect with a JDBC or ODBC driver, Ignite is very convenient to use for data query and data analysis, and can easily integrate with products like Tableau, for example, for data visualization. However, at Ignite, we're also actively working on adding DDL and DML functionality, because SQL is important. And once we do, and it's planned this year, I think we'll come pretty close to being both a data grid, a compute grid, a service grid as we provide, and also a database in memory. So we're trying to support as many use cases as possible. And SQL we've supported from day one. So adding updates or data modification or data definition to our SQL capabilities is a natural step forward, natural evolutional step forward for Ignite. And we already have a couple of committers working on it, and the prognosis is that by the end of the year it should be out. And at that time, the jury will be out. Will we be able to match our DBMS systems on performance scale for SQL queries? I think we will. I mean, we're already doing benchmarking on some of these features. They're already looking very good, but do stay tuned and do actually check out Ignite 1.8 and 1.9 when those get released. And last category I'll mention is in-memory data fabric. So what is an in-memory data fabric? Because, I mean, there are memory data grids, in-memory databases, there are also in-memory data fabrics, and some of you probably heard about in-memory data lakes, etc. So there are a lot of names here, but generally speaking, companies are trying to differentiate themselves on features. And a data grid, for example, if you look at Apache Ignite, a data grid is just one of the components Apache Ignite provides. As I mentioned, we're actively working on DML and DDL functionality for our SQL capabilities. So when we have that, we'll also provide database as another component, in-memory database as another component. We also have compute grid. I should probably move to this slide. We also have compute grid, service grid, streaming components, all of those in memory. So an in-memory data fabric is a collection of multiple in-memory components. All of those components reside under the umbrella of Apache Ignite APIs. All of them have similar APIs. But the main advantage comes not just by having this functionality, but having these components very well integrated with each other. It's very important when you use distributed systems to make sure that your data doesn't move. So if you, for example, use compute grid with a data grid, Ignite will automatically guarantee that your computations are sent exactly to the nodes where the data is. If you use a service grid, you can attach a service to a certain data as well. If you use streaming, the data will be streamed to the nodes where it will be eventually stored and processed, so we don't have to do additional hops, which will always slow down the performance. So that's where the main advantage comes. All these components know how to work with each other automatically without any additional effort from the user. Now imagine if you actually took a data grid from one project, compute grid from another, streaming yet from another. How much time would you spend on integrating those projects, and how much time would you spend on making sure that data doesn't get moved, that we collocate as much as possible? And a lot of times I would say it probably is even impossible, because most of the projects do not have pluggable distribution functions or affinity functions, as we call it in Ignite. So I already mentioned most of the features in data grids and fabrics. But essentially, I mean, if you had to summarize, this category would probably involve more than one feature. So it would involve more than one component. So data grid would be just one of the components. Most of the fabrics would have to have a data grid, because without the ability to distribute data in memory, you're really not supporting in-memory computing. So data grid's probably almost a must component in a fabric. But a lot of fabrics will, a lot of products like Fabric will offer also compute grids, streaming, and at GridGain, for example, at an enterprise level, we'll offer security, management and monitoring, administration, and all like data center replication, network segmentation, resolution, etc., etc. So all these components are going to be, all these features are going to be handled by a system, a platform. However, it's also important that you can talk to your data in multiple ways, and that's where it get another difference between a fabric and a data grid, or a fabric and an in-memory database. Because as I mentioned, a memory database, for example, supports only one API. That API is SQL. If you, on the other hand, come look at in-memory data fabric, then it will generally support. Let's take Apache Ignite as an example, because this is the one I know the best, but it somewhat will apply to other products on the market as well. So you have key value API as one of the ways to access data. You have transactions. You do have SQL API, even though right now it's not as rich as in-memory databases, but you do have SQL API. You also have C++, Java, .NET. Now we have added PDO for PHP support. So you also have all these ways, all these various APIs to access the data as well. Then you have ODBC and JDBC drivers. So you can actually connect from different visualization tools or different SQL tools to query the data directly using JDBC or ODBC connectivity. So all that matters. And on top of that, integration with Hadoop ecosystem also comes into play. And within Ignite Fabric, we provide an in-memory file system, yet another component you can use within Apache Ignite, in-memory file system, which is built on top of our data grid functionality and is fully compatible with Hadoop HDFS file system or HFS file system. So you can actually plug our IGFS, Ignite file system, instead of HDFS, and now you can persist to memory instead of disk using standard file system API. There's also in-memory map reduce component, which is also pluggable in Hadoop, and integration with Spark as well. So one of the main features that you will see in a Fabric, apart from all these components, is ability to talk to your data in different ways, something that most of the point solutions will not provide. Again, if you take a data grid, it's a key value API. If you take a in-memory database, it's an SQL API. So if you want more than one way to talk to your data, then you need to look at something bigger, more of a platform, or more of a Fabric approach provided by some products on the market as well. So that's actually it. I'm going to open it up for questions. I think, we're coming to the top of the hour pretty soon, so we'll probably have a few minutes for questions.
Okay. Yep. Thank you so much. Okay, audience, please answer. If you have any questions for Dimitri, go ahead and type them in to the control panel in the GoToWebinar control panel, and we'll get to them. Okay. So the first question is, when will Data Grid support SQL insert, update, and delete operations?
So actually, as I mentioned, the question is probably about Apache Ignite, because I wouldn't know when other data grids would support those operations. But in Apache Ignite, the upcoming release, which will be 1.8, will have inserts, updates, and deletes with workload support in those statements. So pretty much fully ANSI compatible inserts, updates, and deletes. However, that release will not have creates or alter statements, essentially no DDL yet. But in my true hope, and I'm hoping that community will support me and help me with this, is that by the end of this year, we will also add DDL and DDL capability. When we do, you will be able to talk to Ignite using pure SQL without ever touching any API. So if that use case is important to you, it's definitely coming. But even with 1.8, you'll be able, after you have created schema in XML, you'll be able to use purely SQL to talk to your data, in addition to key value, in addition to compute, in addition to everything else Ignite already provides.
Okay.
So I'll just say we're adding, we're not removing, we're not replacing, we're adding. This feature is being added in addition to all the existing features available in Ignite.
Okay, next question. Could you please more clearly distinguish between Data Grid and Data Fabric? In a nutshell, what are the differences?
All right, so the question is how Data Grid is different from Data Fabric. So as I mentioned, I'll probably just go back to this slide. A Data Grid would be a distributed cache with transactional capabilities, usually. So you're able to distribute data across multiple nodes, and you're able to transact on that data, and some primitive compute capabilities on that data. But the main access to that data is SQL. Well, I'm sorry, is key value. So data grid would be identified by key value access to your data in a distributed cluster. Data fabric, as I mentioned, would provide multiple ways to talk to the data. By multiple ways, I would say, I would mention the following. First is key value. Of course, data grid is an important component. Then there is compute and map reduce. Then there is SQL for querying. Then there is streaming. Then there is C++, .NET, usually Node.js, PHP APIs available. Then there is JDBC and ODBC drivers available to talk to your data. You can actually integrate from data visualization tools like Tableau, etc. Then there is also integration with Hadoop ecosystem, where now you can actually use Ignite as an in-memory file system. So a data fabric is a much broader platform than a data grid. Data grid, I would say, is just a component, one component within in-memory data fabric. Data fabric provides many more components. Actually, these are a lot of components are described here, are actually shown here, but this is not an exhaustive list. So many components and multiple ways to talk to your data. Not just one API, multiple ways to talk to the same data. So you can store data using key value API and access it using compute API and maybe SQL API. So, or maybe you want to store it in Java and access it in .NET. So all those type of patterns, access patterns are supported within Fabric, but wouldn't be supported just in a data grid per se.
Okay, next question. Do SQL statements execute map reduce internally?
So the question is how SQL works internally. I would say not map reduce, probably scatter gather or fork join would probably fit better here. So essentially, whenever we can, we'll send the query directly to the node where the data resides. So at that point, the answer would be it's a direct call. Whenever we can't make that determination, we'll go to all the nodes and execute query in parallel on each node, send the result back to client, and do the final aggregation step on the client side. So it's not map reduce. I would say it's fork join or scatter gather, where you distribute your SQL across multiple servers, get the results back on the client, and perform the final step on the client side. Of course, the results go back and forth in a paginated fashion. We're not loading terabytes of data on the client at once. So that would be the answer.
Okay, great. Next question. We have time for just a couple more questions. Could Apache Ignite be used as an event bus to allow microservices to communicate with each other? Would it be an appropriate use case?
So the answer is yes, it's already used in that way. Essentially, you can use it as a unified distributed data access layer. For microservices, you can one of the premises of microservices is that they should be completely independent. So in that case, you would use caches, different caches in Apache Ignite to store different data within those microservices, have it independent from each other. However, the API to that data is the same, the access to that data is the same, and if at any point in some distant future you will need to query data that belongs to more than one microservice, probably would be considered an ANSI pattern, but let's just say you would have that capability in Apache Ignite. You can query data between caches, data that resides in multiple caches, etc. So my answer would be yes. The API is very simple, and you can use it as a unified data access layer.
Okay, and the final question. What are the use cases for data fabrics with Linux containers?
Well, I mean, I would say that use cases for data fabrics with Linux containers probably the same as on Windows or any other containers or any other operating systems. Let me say, I mean, if the question is really about a business use case, then I would say that there are some features in data grid that are not usually met within well-known, within most known distributed architectures. For example, transactions. If you look at distributed architectures, then I mean, immediately a few projects pop into our head. Maybe Apache Cassandra, MongoDB, maybe Couchbase. Uh, I don't know. I mean, there are several like NoSQL systems that are well-known open source projects. Then there's also Apache Cassandra. That's a key value store that is distributed. But those systems, those databases, do not have transactional capability. So if you want to use something like this, where you really need strong transactional consistency, the only option you have is a data grid. Data grid would provide, you can move money essentially on top of a data grid, and we have many financial customers that do just that. So financial use case would be one. Then there's a whole technical company use case where you want to deploy your project on a cloud. You want to make sure that it scales horizontally. You want to make sure that it can provide common data access to all the components deployed in the cloud. You want to have that access secure in multi-tenant fashion. So all those type of projects are also good candidates. All those type of use cases are also good candidates for in-memory data fabric as well. And of course, since this project is horizontal, we don't have a single component that is specific to any type of industry. There's a lot of use cases from all spectrum of the technology and different industries that use Apache Ignite. For example, there are a lot of pharmaceutical use cases because of number crunching in a distributed fashion. We provide that framework and it makes things a lot faster. There are gaming products like companies, some very well-known games are using Apache Ignite as a backbone of their architecture, et cetera, et cetera. So there are many use cases. I would say probably financial and tech would probably be main use cases, but there are many others.
Okay, and this brings us to the top of the hour. Dimitri, thank you for a great webinar. The feedback from the audience has been really great. And audience, thank you for joining us today, and we hope to see you on a future webinar. Thank you, everyone. Have a good evening or afternoon where you're calling in from. Thanks, Dimitri.
Thanks, everyone. Bye-bye.